All right, then let me welcome you to this good seminar. The speaker, the very little introduction since most of you know Yehuda Pinchover from the Technion, and we are pleased to hear him talk today about equal integration of critical processes.
Sorry, Matthias, I'm sorry I have to interrupt you. Can you share the slides in Zoom?
I can't, but I know somebody who can.
Okay, because
okay, so then like once the slides are online, you are.
Thank you. So, first of all, thank you for the invitation, and I'm very happy to see many friends, old friends, and I thank them for coming. My talk is about joint work with Ujal Das, who was my postdoc here for 3 years in Israel and the Technion. And now he's in Bicam, Spain, Bilbao. And Hinek Kovacic from Brescia, Italy, whom I worked for together, and we wrote a paper about weak perturbation of critical quasi-linear operators. So I will explain everything soon. So okay. So the setting. I have to apologize that my talk is not linear, it's not Yeshara, but it is non-linear stuff. But of course, the linear case is a special case when P is equal to 2. So we have a energy functional Q alpha W. Alpha is a parameter, non-negative parameter. V is a NW. For simplicity, we assume that I have a compact support. And you can see that here we have something which looks like Schrödinger operator, but instead of P equals 2, we have general P between 0 and infinity. And the perturbation is by another potential W, also with compact support, and alpha is the spectral, you can call it spectral parameter or coupling constant. And the associated Rayleigh-Ritz variational problem is the following. You take the infimum between Q alpha W and you apply it to function in W1 P0. You can first you do it for U with compact support, C infinity with compact support, and then you go to the limit, and it turns out that this is a natural space test functions, and you divide it by the P power of the LP norm. So you can think on lambda alpha to be the bottom of the spectrum of the perturb operator. Yes? Of course, this is a nonlinear problem, so cannot speak on spectrum, so you can think of this as the bottom of the energy. Okay, the corresponding Euler-Lagrange equation is given, but instead of the Laplacian, you have the P Laplacian, and here it is given, minus Laplacian PU should be here minus divergence of, sorry for the misprint, minus divergence of grad U to the P minus 2 times grad U. Of course, this operator is well known. The problem is that it is not uniformly elliptic, and it has singularity when on the the set of when the gradient of u is 0. Yes, the critical points of u. And okay, so you see the nonlinearity. If p equals 2, you have Schrödinger operator. Otherwise, we shall call it p Schrödinger operator. And this is, you see here a kind of eigenvalue equation. And u can be think of eigen, at least generalized eigenfunction. If you solve this, you can call it generalized eigenfunction. Okay. So again, this is our energy functional, the perturbed one. And the main assumption here is that when alpha equals 0, Q0 is critical in Rn, which means that the functional without the perturbation when alpha equals 0 is non-negative in the sense of the functional on C0 infinity, or CAS, compact support test functions. So this is the non-negativity of the functional. And the criticality means that if you perturb Q0 and you subtract any compactly supported function, non-zero function, then the functional, the perturbed functional QW is not anymore positive. Okay? So you cannot improve the inequality Q0 greater or equal than 0 by Q0 minus W times phi to the P. Yes? If you subtract something, then it is not anymore non-negative. So, and this is criticality. And of course, there are many equivalent ways to define criticality. For example, it implies that lambda 0 equals 0, and that there exists positive function. Not locally, it's in W1P. Actually, it is continuous function and strictly positive, which is the unique positive super solution of the Schrödinger P Schrödinger equation minus Laplacian. The P Laplacian applies to u times v to the u to the p minus 1 equals 0. And so we have a kind of Liouville theorem, a very strong Liouville theorem. It's not about bounded solution, it's about positive solution, but not only the positive solution is unique in up to a normalization, but also it's a unique positive super solution. And I will give some example of it. Yes.
What does the word super solution mean?
Okay, so what is super solution? I have somewhere to write here? It's written. You can see it. So a super solution. So you have a q. I will write q prime u equals to minus Laplacian p u plus v u p minus 2 u. Okay, this is the operator, the Schrödinger operator, p Schrödinger operator. And to be a super solution is just that you apply the operator and you get non-negativity. That's it. Okay. Solution is it when you have equality here. So let me give you an example, a classical example. Take first of all, minus Laplacian u equals 0 in Rn. Okay? Of course, the corresponding energy functional is grad u to the 2. And therefore, it is indeed non-negative. And now you ask yourself whether it is critical or not. It turns out that it's critical. So it's critical if n is equal 1 or 2. Why? How do you check it? One way to check it is to say, okay, general positive super solution are given by the integral of the Green's function, positive Green's function, times measure. But for n equals 1 or 2, you don't have a positive Green's function, okay? And therefore, you are in the critical case. If n is greater or equal than 3, we call it subcritical. You have positive Green's function, which behaves like x to the 2 minus n. Now, let us do another exercise, and instead of p equals 2, we shall take p general p between 1 and infinity. And then, okay, this is p. This is our, and we assume that v equals 0, yes? We take v equals 0 and we ask, and we are in Rn, and we ask when this operator is critical, okay? And the answer is that if p is if okay, p greater or equal than n, then it's critical. For example, p is 2, then you get n equals 1 or 2. Why this is true? Because if you have a kind of a fundamental solution like the Newtonian potential for the P Laplacian, it is P minus n divided by P minus 1. Okay, and this is true for P less than n. And for P equals n, you have log. Like P equals n, you have log x, or minus log x. So since P is less than n, this is the decaying solution. And this is a kind of a Green's function for the P Laplacian. If P is strictly greater than n, this goes to infinity. And therefore, you can prove using something which is called the Krasminski lemma that it's indeed critical. And the same is with P equals n. So it's critical for P greater than n, the P Laplacian is critical, and it follows from the fact that the fundamental solution is decaying at infinity, while if P is less than n, then if P is greater than n, it goes to infinity. If P is less than n, it decays. Okay? So, okay, so let's continue. Thank you for the question, because it helps me to illustrate the situation. Okay, so in general, one can say that if you have a non-negative functional, energy functional like this, if you take the pile of all non-negative functional, most of them will be subcritical. Critical is indeed, one can look at it as the boundary of all non-negative functional of this type. Okay, so the unique positive solution in the critical case is called the Agmon ground state. Agmon ground state, so in the critical case that I mentioned in our example, the critical case, you have unique positive solution and unique positive super solution, and the positive super solution is 1, the constant. Okay? It doesn't decay in the sense, in many sense, but it has some decay properties, and therefore it's called ground state, or Agmon introduced it for the linear case, and then it was generalized by Kirill Tintareff and myself about 20 years ago. Yes.
Also the minimizer of the variational problem?
It's not a minimizer because 1 is not in a reasonable subwave space, yes, a global subwave space. But okay, if you ask, so in what sense it is minimized, there is something which is called null sequence. You see, the minimizer, meaning that you look at Q, say 0 U divided by U to the P, and you take the infimum, yes? And you ask yourself whether you have a minimizer. If you have a minimizer, then indeed this is you get a unique minimizer, and you have equality. That means that you have Q0. Suppose that this is 1, so you will get U to the P equals 0. Yes, you get, okay. What you have in the critical case in general is that you have minimizing sequence, meaning that you have a sequence of function with compact support, say phi n, non-negative, and phi n in C0 infinity. Phi n is in C infinity, such that Q0 phi n goes to 0 as n tends to infinity, and phi n to the p on a fixed ball, say equals 1. So, of course, if you have a minimizer, then this is trivial, okay? And you can, of course, normalize it to this. But if you don't have a minimizer, this is a weaker property. But what happens is that phi n tends to the ground state locally, uniformly. And therefore, this is an important notion. You can get the ground state by not by a minimizer, but a kind of a null sequence which goes to pointwise to the ground state. Okay, so let's continue. So please ask questions because we have a lot of time. And okay. So what is the spectral gap? You know, in the linear theory, you have the bottom of the spectrum, you have also the bottom of the essential spectrum. And if the bottom of the spectrum is strictly less than the bottom of the essential spectrum, you say that you have a spectral gap. The same situation you have here. So recall that our minimization problem is given by this quotient, lambda alpha, is the number. And here we assume that W, recall that phi0 is our ground state, and W is with compact support, and we assume, and we shall see why we assume this, is strictly positive, because we assume that phi W is not sign definite. So it can be negative or even zero. So this is our assumption. And now what is the analog of the infimum of the essential spectrum? So if I look at, oh, sorry. Okay. If I look at lambda alpha, it turns out that lambda alpha is a function of alpha is concave. Lambda 0 equals 0 because it's by our assumption, it is critical. But if alpha is greater than 0, then lambda alpha is strictly negative. So the lambda alpha, if I can draw a picture, lambda alpha is, so this is lambda alpha, and this is alpha direction, and it's concave and decreasing and continuous, of course. And so these are the important properties that we need to mention. And what is lambda infinity? You can call it the bottom of the essential spectrum. Instead of taking the infimum on all function in Rn, you look at exterior domains, BCR, so outside a ball of radius R, and you take the supremum as R goes to infinity, of course, lambda infinity, this quotient becomes bigger and might be, one can say it doesn't, it's non-decreasing at least. But it might be that it goes even to infinity. So you take the Rayleigh quotient outside a big ball, and you look at the supremum and see what is you get, and you take the supremum, and so since W and V are with compact support, it turns out that lambda infinity of alpha for any alpha equals 0. So you have spectral gap for any alpha strictly positive, because as I told you here, lambda alpha is strictly less than 0, and lambda infinity for any alpha equals 0. So you have a positive spectral gap. And from our experience in the linear case, one believes that if you have spectral gap, you have a minimizer. Yes? And this is true also in the quadrilinear case. Okay, so here is a corollary. Okay, so we look at Q alpha W plus lambda alpha, and we ask whether it's critical or not, because this is for sure, this is non-negative functional, energy functional. If we add lambda alpha, then it becomes Q alpha W is negative, but if we add lambda alpha, then it makes it positive. And it turns out that indeed, since you have spectral gap, this operator is indeed critical for any alpha greater or equal than 0. And we shall denote by phi alpha the corresponding normalized Agmon ground state, or just GS. Okay, so so the situation is the following now. So all the points here, yes, lambda alpha is, as I said, Q alpha W plus lambda alpha is critical. Okay, all over this branch. Here it might be that it goes like here, and it is subcritical, but for alpha strictly positive, it's critical, and also by our assumption at alpha equals 0, it's critical. Okay. Okay, we can say more. One can ask what is the behavior of the ground state. Okay, and so outside, since we assume that V and W are with compact support, then basically outside the big ball, we see Helmholtz equation, which is an operator with constant coefficient. So one believes that one can say something about such equation. And indeed, only 20 years ago, there was a paper by Lee and Zhao that phi alpha x behave like what you see here. Take, for example, p equals 2, then you will get the well-known Bessel, modified Bessel function times some power of x. Okay, so you get here lambda alpha, the square root of lambda alpha times x, which is exponential decay, and you have a power correction. Okay, so it is generalization of well-known behavior of the Green's function of minus Laplacian plus a k squared. Okay, so this will play a role in our discussion. On the other hand, for alpha equals 0, as I told you, we have a fundamental solution, and the fundamental solution is given explicitly by power of p minus to the power x p minus n divided by p minus 1. And now you ask yourself whether this is in LP. Yes, and the very elementary calculation shows you that phi alpha okay, so we shall talk about it later, but what we can say that when alpha tends to 0, then phi alpha will go to phi 0. Although, so of course lambda alpha goes to 1, but the exponent is different because the constant here depends also on alpha. And finally you get, but the fact that phi alpha tends to phi 0 comes from the Harnack principle. You can show that you have some compactness, and as alpha tends to 0, lambda alpha tends to 0, and therefore you can use Harnack principle. You are talking about positive solutions, and Harnack principle shows you that at least up to a subsequence, and finally any subsequence goes to the same ground state because of the uniqueness. So we know that phi alpha x go to C0, and we would like to say what is our main aim in this lecture. We would like to study the asymptotic behavior of lambda alpha as alpha tends to 0. Yes, we would like to talk about the behavior of this curve as we approach 0. And the history of this problem, here is just a notation that instead of writing it like this, I write it like Schrödinger operators. And here, by this, I mean that v times u to the p minus 2 times u. Yes, I look at it, it is not only just a potential term, but as an operator of multiplying the potential times this power. Okay. So in the linear case, the asymptotic is known. Barry Simon in 76 first studied the case of the one-dimensional case, and he got this asymptotic behavior of lambda alpha. So it's like alpha squared. Yes, because here we have a square root. So it's not linear, but it's faster than linear. And recall that we are in the critical case, because minus Laplacian is critical in R, phi 0 is 1, and therefore you have here W times 1. And you see that we use the fact that W times the ground state, the integral of W times the ground state to the P is positive. And therefore you get here positive leading term. And then you have other things. So Barry Simon actually didn't assume that the integral of W is positive. And if it's 0, then you get the second leading term, which is alpha to the 4. Okay. And he also discussed the case of n equals 2 and got this exponential behavior. And let me just say that the method of Barry Simon to get this behavior is using the Schwinger-Biermann principle, he called it. That means he instead of looking at the PDE, he looked at the integral equation, and then he could, since he knows the Green's function, he could compute the asymptotic. So he used the explicit formula of the Green's function in order to get it. Okay, and what happens if n greater or equal than 3? We said that it's the Laplacian is subcritical. So in order to consider lambda alpha, the behavior of lambda alpha as alpha tends to 0, you need to start with critical operator. So what you do, you take the Laplacian and you take these and make this operator critical. How do you do it? You take, for example, V, which is a compactly supported function, but it has some negative part, a non-trivial one, and you use a parameter and then you hit criticality. Yes, you take minus Laplacian plus say beta v, and since v changes its sign, you get beta 0 such that minus Laplacian plus beta 0 v is critical. So this is not an assumption, actually, yes? There are many potentials that makes this operator critical. So, but the starting point is of our study is that we start with critical operator and then we make perturbation. Okay, and Klaus and Simon in 1980 extend the result for higher dimension. And then they showed this behavior for n equals 3, n equals 4, and for n greater or equal than 5, they got linear behavior. And one can ask himself what is special in 4 or in 5? And let me make, how it's called? Let me tell you why n equals 4 is a turning point. It is because n 4 is 2 squared. Yes? So 2 to the 2 is 4, and for n greater than p squared, you get linearity, meaning that things are in some sense better, or you have minimizer. Yes.
Meaning that the Green's function
Is in L2.
L2.
Yes, it's in L2. If you take x to the p minus n divided by p minus 1, then p squared, n equals p squared, is the limiting point where this is not in LP. Yes, if you take this and you make the calculation, this is finite if n is greater than p squared. Okay? Two, yes. And therefore, yes, therefore it's 5 that makes the difference. So this is outside the x greater than r, yes. I'm looking about the behavior near infinity. Okay. So let's see what is known for general P. So Eckhorn, Frank, and Kovacic studied the case, general case P between 1 and infinity, and they look at the case where n is less or equal than P. Why? Because for n less or equal than P, the P Laplacian is critical. And they assume, and then, as we said before, you have uniqueness of positive solution, and the only solution is a constant, so they took the ground state as 1. Okay, what is the result? Suppose that n is less or equal to P, and the potential is 0. That means that we are in the critical case. And now you have to divide into two cases. If n is strictly less than p, you have this power-like behavior. So it's superlinear. Yes. And you get a precise asymptotic in the sense that they got the constant here, the precise constant, which is related to the Sobolev inequality. And this constant doesn't depend, it's a universal constant, depends only on NP and not on, you don't have V. So yes, it's pure constant. And if n equals P, then you get a log term. Because if you put here P equals n, then of course this is not defined. Okay, and you get this log thing. Okay, and again, the constant here is precise. Is n times the surface area of the unit sphere to the power 1 over n minus 1. Okay. Now, since we know how phi0 behaves, we can see indeed that phi0 is in LP if n is greater than p squared. See, this is the calculation. Because, and look that here we don't assume that V is in with compact support, even if we know this and this, what we call Fuchsian type condition, we know exactly how the ground state behaves. And it behaves like a power, and the power is indeed what we calculated, and indeed, so you can guess that you have a minimizer for in the case n greater or equal than p squared. Okay, and this is indeed true. Okay, so now, we are interested in the case n greater than p, or strictly greater than p. And now we look on this. So we have two regions, or three regions. N equals p squared, n strictly less than p squared, and greater than p in order to make it subcritical, and n greater or equal greater than p squared. Strictly greater, sorry. Okay. N equals p squared, and okay. And as we said, since p0 is indeed integrable in LP for p greater than n, for n greater than p squared, then we expect regular or analytic behavior. Where we are, okay. So we assume here we have a result which is we assume that V is in L1 and bounded, and satisfies the Fuchsian type decay. And we assume that this is an assumption. Of course, we can deal with negative one, but we cannot deal with the case, or we don't know up to now how to deal with the case when the integral of W times the ground state to the P equals 0. So it's important to assume this in order that lambda alpha is indeed negative, as you see here. Okay, and then the result is that we have a precise asymptotic. The limit is alpha tends to 0 and alpha is non-negative, is indeed the integral of w phi square phi 0 to the p divided by the p power of the LP norm. Okay. And let me explain the proof because it's quite elementary. So we look at lambda alpha. It is given by the Rayleigh quotient. And we take phi 0 as a test function. Since n greater than p squared, it is a good test function. It's in our natural space. Okay, and I plug it in the Rayleigh quotient. And now, since phi 0 is not the minimizer for lambda alpha, it is greater than lambda alpha. Okay? Okay. Since Q0 phi 0 divided by phi 0 to the p is a minimizer, phi 0 is a minimizer, therefore I have equality. And this is exactly the terms that we are looking for. So we get that lambda alpha is, for any alpha, is less than the required number, as you can say. Okay, so here you see another proof why lambda alpha is strictly less than 0, at least for n greater than p squared. And when we go to 0, this inequality, of course, becomes a weak inequality, but we have inequality, so the lim sup. So indeed we got an upper bound. Yes, so this was very simple. Just take phi 0 as a test function. The lower bound is also not complicated. We know that phi alpha is the minimizer because, as we saw, it is decaying exponentially. So it's in W1P0. Okay, and so this is equality because it's a minimizer. And we write it like this, and therefore Q0 phi alpha is non-negative, so this is greater or equal than 0. But still we have here phi alpha, and this depends on alpha, so I multiply by alpha to the minus 1. And then we have here the integral of W phi alpha to the p. W has compact support, or in L1. So this is finite, and you can go to the limit, and you get in the denominator, you get W times phi 0 to the p. In the denominator, you need to say, okay, phi alpha is less or equal than phi 0, and goes to phi 0 in LP because phi 0 is in LP. So phi alpha is less than phi 0 after normalization. And since phi 0 is in LP and phi alpha is smaller, so it's both are in LP, so it goes to phi 0. The P norm goes to phi 0, and you have this. And therefore, you get a lower bound, and finally, this implies that the limit exists and equals to this. Yes. Okay, I told you that when you have a spectral gap, then it's positive critical. Okay. This is from criticality theory. This is the best way to convince you. Yes, if you have a spectral gap, then at lambda alpha, you have minimizer, okay? So this is the simplest way to do it. Also, or you compute, but you don't have to compute, okay? Okay. Now we are in more difficult way when we don't have minimizer at phi0. And but we can say at least a rough estimate is that lambda alpha goes to 0 faster than linear. And this is also very simple. So phi, suppose that p is less than n. N is bigger than p and less than p squared, where we don't have a minimizer. Here we assume that V and W are with compact support. And we assume that our operators, yes, minus Laplacian plus V, the unperturbed operator is critical. And again, that the integral is positive. W phi, everything as before, except that we are dealing with this interval. Then we say that lambda alpha divided by alpha goes to 0, meaning that it's faster, that it approaches 0 faster than linearly. And recall that for p equals 2, we got a log. It's almost linear for when p equals p squared equals n. Okay. So again, at lambda alpha, for alpha strictly positive, the minimizer is achieved by phi alpha, and we know, so we have equality here. But Q0, the Q0 is non-negative, so this is smaller. The right-hand side is smaller because the Q0 phi alpha is non-negative. Okay? As we saw before, actually. Now again, we assume that phi alpha all are normalized by being 1 at 0. And then I use, again, Harnack convergence principle. Phi alpha goes to phi 0, locally at least. And we recall that phi 0 is not in LP if P in this interval, as we saw. Hence, W phi alpha to the P, since W has a compact support or W tends is decaying fast, the limit is W phi 0P. On the other hand, the alpha norm of phi alpha, the P norm of alpha, phi alpha goes to infinity. Okay, so the limit is infinity, and therefore you get that lambda alpha is greater or equal this number, and since the denominator go to infinity, this go to 0. So we got that indeed the limit is 0, and we got a fast, superlinear behavior of lambda alpha.
How do you get the limit input that you have?
Yeah, actually, it's the lim. So, phi alpha goes to phi 0. Yes, phi 0 is infinity. The integral is infinity.
Ah,
Okay, and yes, so it's just you can do it using Probably, oh, but two lemma or something like this, yes? Phi0 is greater than phi alpha. But yes, okay. Mhm. Yes, you can, yes, by comparison. Okay, now the main theorem is, as I told you, we are interested in n between p and p squared. And here is the main assumption that the integral is strictly positive, and therefore, indeed, lambda alpha is strictly less than 0. And here is the behavior. It's a polynomial in alpha when n is less than p0, and when n equals to p0, you get a logarithmic behavior. And let me just say that, remind you that for n greater than p0, p squared, or equal to p squared, this was done by Frank, Kovacic, and Ekman. Yes? So we have the full picture of the behavior of lambda alpha. And I think that let's skip, if you don't mind, let's skip the.
I don't know if like some people believe that four,
Yes.
like you have to look at
No. I know. Let me finish my sentence. I think that I have at most 1/4 of hour left, and then we shall stop at 3/4. Yeah. Yes, and we shall not do a break.
We have an extended play at the next Wednesday.
Yes, because it's 1 hour. Yes. No.
Like the plan is to go into order past.
Yes.
And then.
Yes.
Okay.
Is it okay?
Yeah, I think so. Like some people in Zoom might need that too, but.
Okay.
But
Ah.
look at them.
Yes. Feel free. Okay. So I think that the theorem is clear, and how we do it. And I will prove it for special interval between 2 minus 1 over n, and so n is greater than p, and p is not greater than 1, but greater than 2 minus 1 over n. Still, we have to prove things also for other p between this number and 1. But the proof is about the same. So I will give you the proof only on this interval of p greater than 2 minus 1 over n, and n is in this interval. Okay. So we take, for any alpha, we take a test function. Actually, it's not a test function, it's a guess for positive subsolution. Okay. Why it is subsolution? Because subsolution, if you can guess that subsolution is below a solution as it is for subharmonic function under some conditions. You have to be careful. Of course, this is true that subsolution is below super solution in bounded domains. In Rn or in unbounded domain, you have to be more careful, and the subsolution has to be decaying subsolution in some sense. And okay, so it turns out that, and you see that this form of function is very similar to the estimate that I gave you in the beginning of P alpha. Instead of the exponent is actually the same, except that you have here something which decays faster. You have this factor 2, which makes it even decaying faster. It turns out that this is indeed a sub-solution of this equation. And phi alpha is a solution, so it's a super solution. And since, as I said, about super solution, you don't have any restriction. Any positive super solution can be compared to sub-solutions, but which are decaying fast in some sense. So since W alpha indeed decays near infinity, you have a comparison principle, and like Fragment-Lindelöf principle that you have for harmonic functions or more general situations. So you have this. And now you make the calculation. You take W alpha and you put it in the Rayleigh quotient. So you need to check how the LP norm of W alpha behaves as a function of alpha. And since phi alpha is greater than W alpha up to a constant, then you can have a lower bound for phi alpha. Now, W alpha is some homogeneity in lambda alpha when you take the integral, and therefore you get this power. Okay, this is just, you take the integral, you take the LP norm to the P, you make the integration, and you change the variable, and by changing the variable, you get this factor. Now, lambda alpha is, of course, bigger than only the last term, because the other term is non-negative. Okay? Lambda alpha equals to the quotient of the minimizer, and now I take away the non-negative term, and I am left with this, and then I am left with this term, and this actually finishes the lower bound. Okay. This is the lower bound, and of course I need to deal with P which are smaller, and what we are doing is that we can find a sub-solution for P less than n plus 1 divided by 2, and the sub-solution has similar form. Instead of this ni 0, we have another ni, and instead of 2, we have beta, but in any case, the proof is similar, and also for n equals p squared.
But I don't understand. So the last inequality you are getting, the lambda alpha is bigger than or equal to something, and then
So UR is alpha, yes?
then you have a lambda alpha.
Yes, so you move lambda alpha to here, you get some power. Yes, 1 plus this power. And Okay, so
The C is actually C2 from 4.
So you get a power of lambda alpha divided by alpha is greater than W this, and but you are interested to know lambda alpha, so you take the root. Yes?
And yes, but we don't have here the final line. What is the lambda alpha?
No, I didn't do the calculation, but it's trivial. Yes, how do you do it? You
Yes.
move it to here and divide it. Okay.
You're still applying the assumption. of
You see, you still have it minus. Oh, sorry. You see, pay attention that you still have a minus, so you have to be careful on the sign, but basically you get lambda alpha to some power divided by alpha is greater or equal than this number, yes? Or keep sorry. No, and then you take the not the square, the root of this, and you get here
No, because
a
lambda
power.
alpha itself is negative.
Lambda, therefore you have minus.
Not there.
Yes, but you have to change, yes? Okay, so it go, yes, you take, you multiply by -1, you get minus alpha also here. You have to be careful, yes, as I said. Okay. The upper bound is just, as we saw, the lower bound comes from potential theory, comparison principle, such maximum principle, you can say. And the upper bound is purely variational. You take a test function, which is which is 1, and it decays exponentially. It's 1, and then exponent e to the minus x. And you enter 2 parameters, our alpha parameter and t, which will be computed later. Okay? And you apply f at the point t times alpha to the p-1 divided by n minus p. This is the power that already appeared, times x. So as alpha goes to 0, t is fixed. Alpha goes to 0, then f is basically 1 for very large x, yes? Since this is small, alpha times p-1 divided by p minus p goes to 0, then x, even for big x, you are in this domain, so it's 1. So that as alpha tends to 0, it goes, f of this function goes to 1. Okay? Okay. And now, therefore, we can get that w as alpha tends to 0 for any t greater than 0. W times f alpha t to the p times phi 0 p goes to w phi 0 p. Because w has a compact support, there is no problem here. Yes? So you integrate 1 times w times phi 0 to the p, and this is a fixed number, w. This is our assumption that this is positive.
But this is by assumption.
Yes, yes. And now we have to estimate Q0. Yes, this what the and also since this is our test function f alpha t times phi 0 p, yes, we need to look at Q0F alpha t minus alpha times W phi 0 P divided by the LP norm of F0 F alpha t times phi 0 to the P. Now, the problem is that it's difficult to estimate it because we have sign changing term. V is sign changing. And how to overcome this difficulty is by something which is called the simplified energy, which is equivalent. So what we know that so you see Q0 is non-negative, but it includes Q0 phi is equal to grad phi to the P plus V to the phi to the P. And this is not sign defined. Yes, it might be negative. So it's difficult to get any upper or lower bound. Yes, doesn't matter. But what is our tool is that QFS, Q0 of say W times phi 0, or W is not V, V times is equivalent, two-sided equivalent to the integral of something which is, you can call it energy functional, but it is not convex, although it include only positive terms, but it's not convex. And it is P0 to the P, okay, grad V squared times phi 0 to the P times grad V phi 0 plus grad phi 0 V.
Say grad P or grad V?
Grad V times phi 0 P, 2, sorry. Grad V times phi 0 P, grad V squared times phi 0 into 2, and then you have this term, grad V phi 0 plus grad phi 0 V to the power P minus 2.
Where did you get the grad V from? You do it in the
Because you have to take the derivative of V times grad phi 0. Yes? So it's a Leibniz rule.
okay.
Yes, it's Leibniz rule.
Yes, sir.
Yes? But you don't see V. You don't see the potential. You kill the potential. It follows from something which is called Picone identity. Okay. And from this equivalence, and you see that P less than 2 is problematic because then you cannot open it and estimate it by sum. Yes, because this is negative. This is negative power when P is less than 2. So you have to be careful, but at least for P greater than 2, you have upper bound by exactly these two terms. You multiply this by this and that's by this. You get exactly what I wrote here. And on the other hand, upper bound, it's enough to take this term. Okay, so we need to, instead of dealing with this ugly term, which we cannot estimate, actually, we need to estimate non-negative terms. And here are the calculation of each term. And you plug it inside, and we know already how this behave. We know by these estimates, we know how this behave, and we know how this behaves, because this is here. And we make the calculation, and we get something which depends on t. And omega is the fixed integral that we have which depends on w, capital W. And now you optimize. You take the derivative and you get the maximum of or the minimum. Sorry, minimum of this function of t, and you get the right exponent. That's it. Okay, and here is the table of what we have. The first two lines are due to Ekholm, Frank, and Kovacic, and these are our contribution. I must say that Frank et al. Are more successful in the sense that they have the precise asymptotic behavior. We have only two-sided estimates. Okay, so except here, we got the asymptotic. For both things here, we unfortunately couldn't find the asymptotic. This is one question that we hopefully will be able. I don't know how to do it, let's say, and another thing which seems to be more difficult is to deal with the case when the integral w phi 0 is zero. Yes. So I thank you for attention. Thank you.
So for the talk, are there questions? Audience?
Again, I try to insert the broad B.
Yes.
You have, so, but you're not assuming any smoothness for differential